Okay, and Sumit, maybe we can begin now.
Okay. Sure. Let me share it. Okay.
Okay, so welcome everybody to this week's Majorana-Raychaudhuri seminar series. Our first speaker today is Sumit Ghosh from Maulana Azad National Institute of Technology, Bhopal, and he's going to talk about non-standard neutrino interactions mediated by light scalars. So maybe I'll send you a reminder when 5 minutes are left.
Okay, yeah, sure. Okay, so let me start. So good afternoon, everyone. So today I'm going to talk about a scenario where we consider the non-standard neutrino interactions mediated by light scalars, and we study the impact of these non-standard interactions on neutrino oscillation experiments. So specifically, we took Dune as a case study. Okay. So we know that neutrino mass and the oscillations is a very well-known phenomena and indicates new physics beyond the standard model. However, the neutrino mass generation mechanism is still unknown. There are plethora of models that can produce neutrino mass, but we exactly don't know which one will be the right model that can produce the tiny neutrino mass. But all this new physics in the neutrino sector that we propose to generate the neutrino mass can also give rise to non-standard interactions of neutrinos. Now, these non-standard interactions of neutrinos so far have not been found experimentally, but if we can find them in the experiments, that is, if they exist, it's a direct proof that new physics beyond the standard model exist, and we can kind of get a form of new physics beyond the standard model. So, from a phenomenological point of view, these non-standard interactions of neutrino is very important in the context of neutrino physics. Now, in literature, we can find there are plethora of studies where people studied the non-standard interactions of neutrinos mediated via mainly the vector boson, specifically the heavy vector boson. But recently, in 2019, the non-standard interactions mediated by a scalar was brought into limelight by this group, Xiaofeng and Stephen J. Park. So this area is still less explored, and so we thought it's a good idea to explore the scalar non-standard interactions and study its impact on the neutrino oscillation. So what do? We consider a light scalar mediated NSI, which can arise from a UV complete model that can give rise to a light scalar. And we want to study its effect on neutrino oscillation, specifically on the neutrino oscillation parameter, the CP violating parameter, CP measurements at long baseline neutrino oscillation experiment, such as DOOM. So we want to find the sensitivity on the NSI parameters, considering all NSI parameter non-zero at the same time. Unlike the previous studies in the literature where people usually consider one parameter at a time or maximum two parameter at a time. Now here we will consider all parameters non-zero at the same time. And we find its impact on CP measurement at Dune by introducing a model-independent parameterization. Now, finally, we want to translate the sensitivity on the NSI parameters to the sensitivity on the more fundamental parameters of the scalar models and on the parameter space for the light scalar model, and compare this parameter space with the existing non-oscillation probes such as ineffective BBN, electron neutrino scattering, and other probes that we will talk about later. So before I start showing our results, let me briefly mention what do we mean by the scalar NSI and how do we parameterize the scalar NSI for our calculations. So the scalar NSI between neutrinos and the standard model fermions can arise from Yukawa type interactions that connects the light scalar with the neutrinos and the fermions. Now we can show that the effect of this phi on neutrino propagation is equivalent to changing the neutrino mass by calculating the equation of motion of the neutrinos. So here m nu prime is basically m nu plus delta m nu. This delta m nu is the correction term to the neutrino mass due to the presence of the scalar NSI, where this delta m nu is directly proportional to the Yukawa coupling that connects the neutrino with the light scalar and the value of the scalar field. Now, this correction to neutrino mass also modifies the neutrino oscillation Hamiltonian compared to the standard interaction Hamiltonian that we see in the standard model. Now, the striking feature of this modified Hamiltonian is the last term, where we have a term like m nu and delta m nu, the product of m nu and delta m nu. Now, in next slide, I will show that this ensures that this Hamiltonian propagation will actually depend on the absolute mass scale of neutrino, unlike the standard interaction case or the vector non-standard interactions. Now, we can estimate the mass correction delta m nu in terms of the Yukawa coupling and the matter density by calculating the equation of motion of the phi prime. So this phi prime uh, shown earlier, this y nu phi is induced by the fermion matter density Nf. So the delta m nu, the correction to the mass term, is directly proportional to the matter density. Now this also suggests that we can take the long baseline experiments uh, to study the effect. Basically, this long baseline experiments would be the ideal place to study the effect of these scalar non-standard interactions. Now, in literature, usually people parameterize this correction in terms of the dimensionless quantity eta alpha beta in flavor basis. So, which is the inclusion of the term square root of delta m31 square makes sure that the parameters are dimensionless. Now here you can see the diagonal elements are real while the off-diagonal elements can be complex. One more thing we should notice here that we need total 9 real parameters to parameterize this correction. Now, by this parameterization, we make sure that we can connect the ETA's parameters to the more fundamental model parameters, the Yukawa couplings, through the following relation that includes the scalar mass and the matter density as well. Now, before we show our new parameterization scheme, let me briefly mention some of the striking properties of scalar NSI. So the first property I will mention is the oscillation probabilities when NSI, scalar NSI are present are sensitive to absolute mass scale of neutrinos. This can be easily understood by comparing the propagation of psi, which gives the probability of getting nu beta type of neutrino in the time propagation of nu alpha for standard interactions and the scalar interactions. Now, if we look at the first expression on the top for the standard interactions, we can see in the second bracket, there is a term proportional to mk square over 2m nu. So we can subtract an identity matrix that is proportional to the lightest neutrino mass and write the whole expression in terms of mass square quantities delta m square a1. That is very known result. We know in neutrino experiments, we usually don't measure the absolute mass of the neutrinos, but we measure the delta m square. But in the presence of scalar NSI, even after subtraction, we have a terms of the form m times delta m. So this term tells you that now the propagation of psi will depend on the absolute absolute mass scale of the neutrino. Another interesting feature of scalar NSI is the presence of unphysical phase parameters that have physical consequences on the neutrino oscillations. So from standard model, we can see that the leptonic charge current weak interactions give a current that connects leptons, neutrinos with the W bosons. Now here, when we want to diagonalize the neutrino mass matrix, we can diagonalize it using PL and P nu matrix, which are basically unphysical diagonal rephrasing matrices, which can be rotated away in the calculations. But in the presence of scalar NSI, we cannot rotate away the unphysical matrix PL that remains within the calculations, and this unphysical phase matrix can mimic the real phase during the calculation, and that's a problem. These unphysical phases can contribute to the phase of NSI parameters also and can affect the measurement of CP phase at oscillation experiments. So earlier I mentioned that this kind of scalar non-standard interactions can arise from UV complete model. So in an earlier work, we have proposed one such simple model by extending the scalar sector of the standard model. The extended scalar sector includes two doublet H1 and H2 and one singlet scalar phi and a triplet delta. Now we further consider that only one of the doublet will obtain vacuum expectation value, while the vacuum expectation value of the other doublet is 0. Both singlet and triplet will also obtain vacuum expectation value. Now the mixing in the scalar sector give rise to one light scalar. We can call it phi prime, with its mass can be as low as 1 keV or less than that. Now the Yukawa terms that connect the standard model lepton doublet with the triplet and scalar mixing make sure that we have NSI of neutrinos with the light scalar. On the other hand, fermions interacting with the doublet H2 that obtains zero expectation value give rise to flavor changing neutron current at tree level, and scalar mixing then makes sure that fermions, the standard model fermions, interact with the light scalar. So on one side, we have the neutrinos interacting with the light scalar coming from the Yukawa term that connects the standard model lepton doublet with the triplet. And on the other side, we have fermions interacting with the light scalar that's coming from the interaction of fermions with the doublet H2. Now, these two terms make sure that we have non-standard interactions of neutrinos with standard model fermions. Now, for our numerical calculation, we took Dune experiment as a case study. So we measure the effect and find the sensitivity of Dune on NSI parameter space. And in our calculation, we took the baseline length of Dune as 1300 kilometers. We also consider an exposure of 7 years in equal neutrino and anti-neutrino mode. We specifically put stress on calculating the CP violation measurement or the delta CP parameter in the appearance channel of Dune nu mu to nu e appearance channel. So now the mass correction term, oscillation parameters of the oscillation experiments are sensitive to mass squared matrix. Now we have the mass correction term added to the mass matrix also. So that will be very difficult to handle numerically. So that for that reason, we introduce a model independent parameterization. This model independent parameterization makes sure that we can turn on all the parameters at the same time and we can have a solid numerical result. So in the top right corner, the matrix in terms of the mu parameters are our new parameterization scheme. Now here, if you see, we only need 8 parameters. Now earlier I mentioned in terms of the eta, we need 9 parameters. So if we make some scheme that can map the eta parameters to the mu parameters, so in the mu parameters, eta parameter space, we have redundant parameter. So later we will, when we do the actual mapping, in that case, we have to fix one parameter to make sure that there is a proper mapping between the two parameterization scheme. Now, in the following, we have the equations that connect the mu parameters to the eta parameters through these epsilon parameters, which is defined. So, in the top left corner, the delta m equal to this delta m is in the mass basis, where this delta m, this thick m, is the one in the Kleber basis. So once we have the reparameterization scheme, then we can demonstrate how the oscillation probability will behave under the presence of non-zero, non-standard interaction parameter. Now, on the left-hand side, we don't see any interesting feature. The black solid line in the middle show the probability depending on the delta CP parameter for the usual standard model interactions, while the colorful lines correspond to different eta EE values. So here we are considering only one parameter. Now, on the right side, we turn on the eta E mu parameter. Now, here we have some interesting feature. You can see for a few values of delta CP, we have degeneracy in the NSI parameter. So multiple NSI parameter can give rise to the same value of delta CP. So in principle, this degeneracy will cause or diminish the power to measure the CP violation parameter delta CP at dune. So we calculate the effect of this degeneracy on the calculation of delta CP parameter. So for that, we took the standard value for the various oscillation parameter without considering any new physics as the true values for our numerical calculation. And then we find the CP precision measurement result or the power to calculate the delta CP at the dune. And here the solid lines, the solid blue line correspond to the normal ordering, and the solid orange line correspond to the inverse ordering, while this dashed blue line correspond to the normal ordering without any NSI, and the orange dashed line correspond to the inverse ordering without any NSI parameter. So as you can see, the presence of NSI parameter, the solid lines is relatively less powerful compared to the one with the without the NSI. So that is because of the degeneracy shown in the last plot here. So the degeneracy in the NSI parameters basically diminishing the power of calculating the delta CP parameters. Now next we calculate, turn on all the parameters at the same time and calculate the sensitivity region of the SNSI parameter at dune. So here the diagonal subplots show the marginalized distribution of each parameter, and the off-diagonal subplots show the two-dimensional marginalized distribution and the dark region show the 68% confidence level, and the shaded region or the light shaded region represents a 95% confidence level intervals of the parameters that can be probed by Dune experiment. Now here we first show the parameter space, sensitivity space in terms of the mu parameters, and then by setting a parameter. So for example, we set the epsilon 1 equal to 0 and map it to the eta parameter space, because ultimately we need the parameter, the sensitivity plot in eta parameter to connect it to the Yukawa parameters of the model. So here is the plot, same plot for the eta parameters, which you got by using the mapping between the mu parameter and the eta parameter. Now these two results are for normal lettering or ordering. Similarly, we obtain results for the inverse ordering for mu parameters and the eta parameters. Now in summary, we show the range of various parameters for normal ordering and inverse ordering that can be probed by Dune. Now, for some of the parameters, you can see it has a very large range, while few other parameters like eta, E, mu have a very narrow range. So uh, that will basically give degeneracy in the calculation of delta Cp. Now, finally, we translate these eta parameters into the model parameters in terms of the Yukawa coupling. So first here we show the electron coupling and the neutrino coupling. And here the blue dashed line show the sensitivity curve obtained from the oscillation experiment at Dune. Now, other constraints here involve the red lines that include everything, that electron neutron scattering experiment, fit force search, BBN, early universe cosmological constraint like delta and effective BBN, etc. And this orange line and the green lines are directly related to this neutrino non-standard interactions. So we saw that the scalar mediated non-standard interactions correct the mass term of the neutrino by adding a mass correction. Similarly, they will also correct the neutrino mass matrix in the presence inside a sun or supernova, basically high density region. So Borexino data can put constraint on this in medium neutrino mass coming from the scalar non-standard interactions that correspond to this orange line, and the supernova SN 1987A data can give constraint for the neutrino mass inside the supernova. That is the green line. Now, what do we get from this plot? The parameter space that's sensitive to Dune oscillation experiment is currently already ruled out by all these known other non-oscillatory experiments. So earlier when we said that the SNSI or the scalar non-standard interactions, the presence of scalar non-standard interactions at Dune can mimic the CP effect because of these unphysical phases and can hinder the accurate measurement of the CP, delta CP parameter at the oscillation experiment. But we ultimately find that the parameter space sensitive to Dune is already ruled out. So it will not be a big issue if the SNSI is present while we measure the delta CP at Dune. Similarly, we obtain a similar plot for neutrino and nucleon interactions. But here are some catches. So when we consider all these constraints, we only took the constraint from literature. We did not do a complete analysis of this constraint by turning on all the scalar NSI parameters at the same time. But our blue dashed line is the effect of all the scalar non-standard interactions parameter non-zero at the same time. So a proper analysis would be to consider constraints based on these multi-parameter calculations. So our work in a nutshell. So we consider a light scalar mediated NSI that appears as a correction to the neutrino mass term. Now, this scalar mediated NSI can have unphysical phases, and that can have physical consequences on neutrino oscillations. The CP measurement and neutrino long baseline oscillation experiment, such as Dune, can be impacted by the presence of light scalar mediated NSI. So we measure the Dune sensitivity on NSI parameters, considering all parameters at the same time by introducing a more friendly parameterization scheme. Then NSI parameter sensitivity were translated into sensitivity on the parameter space for light scalar models and then compared with existing constraints. We found that the scalar parameter space, which Dune can probe, is entirely constrained by current data. Okay, thank you. That's the talk.
Okay.